Welcome, everybody. Thank you for joining us today on this wonderful Thursday. Today's presentation, we will be introducing Fana. Fana is an open source feature flag management platform that allows developers to test new features in production confidently. First, I'd like to introduce the team behind Fana, Yoorhim, Rob, Juan, and myself, Audrey. And we've worked extremely hard on this project and are quite proud of what we've been able to accomplish these last few months. And you'll get to hear from each of them throughout the presentation. So before talking about Fana, we're going to talk about the problem space that inspired Fana, where Fana fits in as a solution to this problem, and the engineering decisions we made while building the application. We'll also have a brief discussion about some potential future work at the end. So first, I'll dive into the problem exploration and talk about some of the challenges of testing new features in production and why testing is important for building confidence in future releases. When releasing a new feature to end users, developers want to be able to release that feature with confidence. This means bug-free with a minimal risk of unexpected behavior. One way to increase confidence is to use automated testing suites in a deployment pipeline. Testing helps verify that an application as a whole behaves as intended. This is especially crucial as new code is being contributed to the codebase on potentially a daily basis. Automated testing can help prevent regressions or break things that previously worked. Another way that developers can increase confidence when releasing a new feature is to use staging environments. Staging environments are meant to be a near replica of production environments to ensure quality under a production-like system. The main benefit of testing and staging is that if something breaks, it doesn't affect any real users. So in summary, testing is the foundation for developers to be able to move fast with confidence. Despite extensive testing in pre-production environments, things can still go wrong in production. Why is that? Well, testing is about reducing uncertainty by checking for your known failures, your past failures, or predictable failures. These are your known unknowns, things that you can write tests for. What you can't test for are your unknown unknowns, race conditions, network unreliability, and most importantly, it's really hard to predict how your users may behave. So the combination of production system infrastructure and unpredictable user behavior makes it extremely difficult to test and guard against all possibilities in a controlled environment like staging. So here I have a quote from Charity Majors. She's the co-founder of Honeycomb, and she sums up this idea pretty well. She says, once you deploy a feature, you aren't testing code anymore. You're testing systems. A system's resilience is not defined by its lack of errors. It's defined by its ability to survive many, many, many errors. So if testing in pre-production systems doesn't guarantee bug-free feature releases, and errors and bugs in production systems are inevitable, how can devs build confidence in their application's resilience? In other words, how can developers responsibly test a new feature in production with real users? So developers need a way to minimize the impact on end users if something goes wrong. There are three key strategies to enable this. First, release new code to a small group of users first, and then isolate that feature causing the issue. And third, roll back the application to a stable state. Let's dissect this first criteria a little bit further. By releasing a feature to a small group of users first, then gradually increasing the number of users exposed over time, developers can limit the total number of users impacted if any problems arise. To take this strategy a step further, developers can target specific types of users, starting with the most bug-tolerant subset of the user base. Examples of this include users internal to the organization, also known as dogfooding, and then releasing the feature to beta users or early adopters, and eventually all users. To make this idea of testing and production a little bit more concrete, I'll briefly talk about a case study. The engineering team at VMware, a cloud computing company, wanted to rewrite an important, highly visible feature of one of their applications. Their team had 3 goals in mind for deployment. First, investigate real user issues in production. Second, evaluate feedback from those users. And third, limit the impact of any bugs on the user base. So to achieve this, VMware first released that feature to only the developer team to test it in the live production environment. Next, they released the feature to external beta users. They developed and tested new iterations of the feature based on those users' feedback. Only after several iteration cycles did they finally release it to the general audience. So VMware's engineering team used a progressive rollout strategy to target specific users to facilitate testing and production. Using this strategy, they were able to meet their goals and deploy the new feature with confidence. Now that we've discussed how teams can test in production responsibly, we'll explore 2 common approaches to accomplish this: multiple deployments and feature flags. A multiple deployment strategy, also known as canary deployments, utilizes a second production environment that hosts the application with the new feature and uses a load balancer to route traffic between those 2 production versions. So in this visual, we have about 95% of users being routed to prod version 1 and 5% of users being routed to prod version 2, or the environment that's hosting that experimental or new feature. So what are some of the benefits of this strategy? First, a cleaner code base. Routing logic is abstracted to the load balancer. So each environment is solely responsible for serving one version of the application. This ensures new versions won't contain code references to older versions. Next, there's no downtime to users. If a rollback is needed, developers can reroute all traffic from prod version 2 back to the stable prod version 1. Last, developers can configure the routing logic in the application load balancer to route users to specific experiences. So let's consider some of the trade-offs. Developers cannot selectively roll back a specific feature in a given deployment. For example, if 3 new features are included in the prod version 2 deployment, but one of those features is not performing as expected, the entire application, including those 2 satisfactory features, would need to be rolled back. A second trade-off to consider is the additional infrastructure resources needed, since there is more than one production environment online. This has cost implications and adds complexity in order to monitor and maintain that additional infrastructure. Furthermore, if a need arises for more versions of the deployment, developers would need to deploy more environments to test the different variants of the application. This can compound the cost, complexity, and overhead of maintaining multiple production environments. Next, we'll take a look at what feature flags are and how they can be used as a tool for testing in production. A feature flag strategy at the lowest level consists of conditional statements that determine whether or not a given block of code should be executed. This can be used in a front-end or back-end application. So in this code snippet example, we have an if-else statement that controls the logic flow of the app. If the evaluate function for the new feature evaluates to true, then it will serve the new feature. Otherwise, it'll serve the old feature. So what are some benefits of using feature flags? Feature flags allow selective feature rollbacks. Each new feature is tied to a single flag. Going back to our previous example on the last slide, if one of the 3 features in a deployment is buggy, the developer can simply toggle off that one feature while the others stay on. Next, zero downtime. Feature flags rely on the conditional flow in the source code itself, which allows them to be configurable remotely. Code does not need to be redeployed to change the routing or evaluation logic. Third, feature flags can target users using logic or data accessible in the application itself, such as what users logged in, and use these as inputs to the evaluate flag function and determine the flow of the conditional block. And of course, we have to consider the trade-offs here. So first potential trade-off is technical debt. Because the conditional logic lives in the application code, the extra code adds maintenance complexity to the code base. This necessitates increased coordination between teams, including managing the status of active or inactive flags, understanding when old flags can be removed from the code base, and who has ownership over the governance of different flags. Another trade-off to consider is that feature flags can add to page load times. Feature flags like the evaluate flag function in our snippet are remotely controlled over the network. Network latency and faults can affect the loading time of the application relying on the result of that feature flag. So which approach best fits our use case? As a reminder, our criteria for testing in production responsibly is giving developers the ability to target user groups, roll back the application to a stable state, and isolate the buggy feature. So let's compare the two strategies. So for targeting users, in both strategies, we're able to do this just in different ways. Multiple deployments, this is done at the infrastructure level, whereas for feature flags, this is done at the application code level. Next, rolling back the application state. Again, both are able to achieve this with no downtime to users. Multiple deployments does this by rerouting 100% of traffic back to the stable production version, while feature flags, you simply toggle off the flag to change the application logic. Third, isolating the feature that needs to be fixed. In a multiple deployment strategy, this requires a full rollback of the deployed version of the application that contains the buggy feature. In a feature flag strategy, you can selectively disable a specific feature flag because each feature is wrapped in its own flag. So for this criteria, using multiple deployments does not allow developers to solely isolate the problematic feature, since an issue with one feature impacts the deployment of other features. So because feature flags meets all three of our criteria, feature flags is a better fit for our use case of testing in production. Now I'm going to hand it off to Juan, who's going to take us on a more in-depth look at feature flags and how they can be used to responsibly test in production.
Thanks, Audrey. So we'll be exploring feature flags as a solution next. One of the defining abilities of feature flags is the ability to toggle functionality. Most implementations allow this to be reflected in real time, allowing for any updates to instantly be reflected on the client or server side. In this visual, you can see that when the Google Pay option flag is toggled on, the page displays the Google Pay button, and when it's off, it displays the standard credit card payment option. So toggling is a key and useful feature of feature flags, but it alone isn't enough to safely test in production because it indiscriminately affects all end users, rather than just a bug-tolerant subset. Feature flag implementations also commonly allow targeting specific users based on attributes. Attributes are made up of user traits, like state of residence and whether they are a student, like you can see on the left side. For example, if we wanted to target any users who are students on the US West Coast, we can set up a feature flag to target users with a student attribute value of true and a state attribute value of California, Washington, or Oregon, and you can see these targeting rules in the middle. The feature flag code would then compare the user attributes against the targeting rules and determine whether to evaluate to true or false. This evaluation would then be used by the developer to determine what experience to serve. So in this example, Audrey is a student in Washington, so she passes a targeting rule and she gets served the new feature. Juan is in California, so he fulfills the state requirement, but he is not a student, so he gets served the old feature. To take attributes one step further, some feature flagging platforms also allow the creation of audiences, which are essentially bundles of reusable conditions. They functionally work the same as general attribute targeting, but audiences provide the convenience of reusability, and they allow for idiomatic naming, which makes it easier for other developers to understand who the flag is for. In this visual, we have 3 users being evaluated to see if they're part of the West Coast students' audience. This audience is just an abstraction of the conditions we saw in the previous slide, but other developers can easily take a look at the audience being targeted to see what the intent is. Next, let's take a look at some of the options developers have to start making use of feature flags. One option to implement a feature flag platform is to do it yourself and build an in-house solution. To do this, the team would need to build out 3 components at the bare minimum. They need some way to manage the flags, like a command line interface or a dashboard. If you expect that developers will be the primary users of this, a CLI would definitely be easier to implement. They would also need a database to hold persistent flag data, and a code package or an SDK that they can embed in their application to communicate with that database. As an aside, teams can also leverage open source solutions as a starting point for their feature flagging platform, but this will likely still require time and resources to configure to the team's requirements. So DIY can be doable for a small team, but as needs start to grow, it can be difficult to ramp up the development to accommodate evolving needs, like in this case study. So Atlassian built its own feature flagging system primarily to control feature releases. But as more teams wanted to use the in-house solution, developing and maintaining the solution became unwieldy because there weren't SDKs available for every language. In addition, the system was not designed for users outside the development team. Without a UI, teams outside of engineering, like product management, they had to rely on engineering teams to manage flags and run beta tests. Atlassian actually ended up migrating to LaunchDarkly, which is a paid solution, and I'll be getting into that next. So the resource overhead and lead time of a DIY solution may be too prohibitive for some companies, so they may look towards commercial feature flagging solutions on the market. These tend to save time and resources by providing rich and convenient functionality out of the box, like support for experimentation, workflow integrations, audience targeting, and more. 2 of the biggest names out there are LaunchDarkly and Optimizely. So let's compare the options we just covered. DIY solutions are self-hosted, which means you don't have to worry about issues with sharing data with third parties. But while you can configure them however you wish, DIY solutions take time and resources to set up, especially to build out more advanced features like audience targeting and experimentation. Paid solutions, on the other hand, are designed to be easy to set up, and they're feature-rich out of the box. But some functionalities may be gated behind higher payment tiers. They also tend to be third-party hosted, which can be an issue for companies handling sensitive information. So as you can see, there's a need for an affordable feature flagging platform that is able to accommodate testing and production via audience targeting. And here's where Fana comes in. I'll start by comparing Fana to the previous 2 options, and then we'll go a bit into what we call Fana's entities. Fana is open source, so it's a free alternative that provides the ability to target audiences out of the box. However, since the primary goal of Fana is to facilitate testing and production, it doesn't include other features like experimentation and A/B testing. It's entirely self-hosted, so your data stays with you and is not shared with any third parties. It's also very easy to get started, which we will talk about a bit later in the presentation. Next, we'll be demonstrating how to create feature flags. But to understand how to do this, we'll need to take a closer look at Fana's entities. These enable Fana users to target intentional segments within their application. This is a screenshot of the Fana dashboard, where you can create and manage your entities. We're currently looking at the flags, where you can see all of your created flags and their status, which can be toggled. On the left navigation pane, you can see that there are audience and attribute sections as well, which looks similar to this view. To get us started, let's talk about attributes first. As I briefly covered earlier, an attribute is a category that describes a user, and it can also be thought of as a trait or characteristic about a particular user. Fana currently supports string, number, and Boolean type attributes. And in the developer's codebase itself, each unique user should have what's called a user context object generated by the application. It consists of attribute value pairs that are used when evaluating that user's eligibility for an audience. So below, you can see that user context object using the 3 attributes above, each with an assigned value. And here's a short clip of how to create attributes within Fana's dashboard. You can click on Create Attribute, which will bring up the creation modal. You can pick a key and pick a data type, and then hit Create. You can also click into the attribute to see details about it, like what audiences it's being used in. These attributes will come in handy when we create audiences, which I'll talk about next. So audiences are collections of logical conditions, and they're reusable. But what are conditions? They're essentially the targeting rules that define whether a user is eligible for an audience. And conditions are made up of three parts: an attribute, an operator, and a target value. In this example of a condition, any user with a state attribute set to either California, Washington, or Oregon will pass for this particular condition. Audiences can actually have multiple conditions, which means we need to specify how to evaluate them in aggregate. So when creating audiences, Fana users can specify a combination indicator, which can be set to either any or all. If the combination is any, it means the user only needs to fulfill one of the conditions to be eligible for that audience. And if the combination is all, it means the user needs to fulfill all conditions to be eligible. Now let's take a look at how to create an audience within the Fana dashboard's Audiences page. Clicking on the Create Audience in the corner brings up the creation modal, where you can specify a display name and a key. Next, you can start adding your conditions. We're going to create two conditions here. One to pick out the West Coast states. So we pick the state attribute, the isIn operator, and our condition values will be CAWAOR. We save it. And then we also want to pick out the students. So we add another condition, picking the attribute student, the operator is equal to, and the Boolean value true. Since we want both of these conditions to be fulfilled, we're going to set the combination indicator to all. And then we click Create Audience. And you can also click into your newly created audience to see and edit the details. You can also see a list of flags that are using this audience. Since we just created this one, there aren't any, but we'll get there next. Flags are the core entity of Fana. Each flag is meant to represent a specific feature that the developer wishes to test. They consist of four properties. First is a title, which helps the Fana user easily distinguish between flags. A key, which is an identifier string used during evaluation within the application. A toggle, which indicates whether the flag is enabled or disabled. And a list of targeted audiences. A user must be eligible for at least one of the targeted audiences to evaluate to true for this flag. Here's how to create a flag within the Fana dashboard. In the Flags view, you can click on Create Flag to bring up the creation modal, fill in your title and your key. This flag that we're making is going to represent a banner for West Coast students. Next, you can pick out the audiences you want to target, where you can see our newly created West Coast students, and then click on Create. And then you can click into the flag to take a look at the details and make any edits if you need to. You can actually also click into your targeted audiences in case you may have forgotten what conditions it consists of. And you can see our related flag there, our West Coast student banner. And to toggle the flag on, you just need to hit the switch, and to toggle it off, you do the same. Now let's take a look at this real-time toggling in action. Here we can see the Fana dashboard and a simple React shopping application side by side. Our West Coast student banner flag is enabled on the left side. And you can see that this is reflected on the right side, where I'm visiting the page as a supposed West Coast student. But suppose that something were to go wrong. Maybe this experimental banner is causing some sort of system-breaking bug. Well, there's no need to redeploy a generic version. Thanks to feature flags, you can simply toggle it off, and you can see that the banner reverts back to the generic banner in real time. So now that we've covered Fana's entities, I will hand it off to Yoorhim for a technical deep dive into Fana's architecture.
Thank you, Juan. So in this technical deep dive, I will discuss Fana's overall architecture, the responsibilities of each part, and trade-offs we'd considered in making those decisions. In this diagram, the components shown in orange are part of Fana's event-driven architecture, where events like changes or updates to flags trigger communication between the components. The first component is the manager platform. This consists of our UI dashboard that Juan walked us through earlier, where developers can create and manage a set of attributes, audiences, and flags. It also has the Manager API backend, which processes incoming data and writes to the Postgres database. When the Manager backend starts up, or when any changes are made to the flag data, the backend sends a copy of the flag data to our data store layer. This data store layer also serves as a pub/sub service where the manager can publish those flag updates to. The data store layer is also connected to our flag bearer. Our flag bearer is responsible for managing connections from the client application, as well as evaluating flag data. It also subscribes to different channels from the pub/sub and routes or directs the event notification to its destination, which are our client and server-side software development kits, or SDKs for short. You can see here that Fana's SDK, shown in orange, sits within the flag consumer, shown in purple. This is because the SDKs are embedded into the developer's application, and this allows that application to communicate with Fana's platform, enable flag evaluation at the application's runtime, and consume event notifications in real time. Fana provides SDKs for a client-side React app and a server-side Node.js application, and we will discuss some of the differences later in the presentation. So now that we have a bird's eye view of all our components, let's discuss why we have these different components separated out. In our first iteration of the Fana platform, we had the one component to perform all tasks, like serving the dashboard, making queries to a database, managing, validating SDK connections, and pushing event notifications to SDKs in real time. And while we were working with this architecture, we noticed a few things. First, because the manager is handling different types of requests, like requests from the UI dashboard and requests coming from various SDKs, we had to think about engineering decisions for when the application reaches the limit of the server due to increased traffic and even concurrency. Secondly, having all functions in one component introduces a major single point of failure, making our system not a very fault-tolerant one. And lastly, the way we were organizing the functionality in our code base started to organically separate concerns into different modules. So ultimately, applying that principle of separation of concerns would allow our application to be more cohesive and reduce tightly coupled components that depend on each other. A natural breakout point then was to have one component handle requests coming from the developer dashboard and another component to handle requests from the SDKs. So our evolved architecture was born. Now we have the manager platform, serving dashboard and making queries to a persistent database, and a flag bearer to act as a simple reverse proxy for the manager. And this abstracts away some of the SDK concerns from our backend, so like managing connections and sending updates. And having this flag bearer broken out, we now had to decide how will this flag bearer access the flag data. Should the flag bearer reach out to the manager to get the flag data every time request comes in? If we were to do this, then we no longer solve the problem of reducing traffic load to the manager. Another option would be to store a copy of the flag data in memory of the flag bearer. And while this was a viable option for us, we wanted a strategy that would allow us to continue to maintain separation of concerns, where the flag bearer wouldn't have the additional responsibility of managing data and its consistency. So ultimately, our solution was to decouple the data storage with a Redis data store layer. As you can see in this diagram, we now have the Redis data layer sitting in between the manager platform and the flag bearer. The manager will write the most current flag data to the data store when any changes are made to the data. And the flag bearer can now just access data through this Redis cluster instead of requesting them from the manager every time. But aside from responding to SDK's initial requests, we also had to address how the flag notifications will be communicated out to the SDKs as they happen. And for our use case, we needed a way to communicate different types of updates as well. For example, flag toggles for when we are enabling or disabling flags, and also general flag configuration updates. And since pub/sub patterns enable the creation of publisher and subscribers with message channels, we chose to integrate this communication pattern in our architecture. So here's our final evolution diagram shown here. We can see that the Redis serves as a data store and a message broker. And here, if we can follow the red dot, we see that when manager receives the update, it writes to the data store and publishes messages to the pub/sub. And it doesn't need to concern about the consumers who are receiving these messages. It's the flag bearer that subscribes the SDKs to the appropriate channels so that they can receive the messages. The added benefit to this model is that it gives us the flexibility and option in the future to scale the flag bearer layer without impacting how the manager will communicate its updates to the flag bearer nodes. Okay, so we've discussed how Fana is architecturally set up. Let's talk about how we can deploy Fana. In this section, I'll discuss our Docker Compose and AWS deployment options and the decisions we made in choosing them. We have used Docker files to containerize Fana's manager and flag bearer components separately. And containerizing our application allows us to achieve process level isolation. This helps us to reduce any risk of issues like ones arising from version dependencies, for example. It also allows flexibility of deploying and managing Fana components in the environment of developers choosing. So developers can then deploy Fana using a Docker Compose file, which references Fana's latest images for each component, as well as the Redis and Postgres images as well. Docker Compose is helpful here for two main reasons. So by design, containers run in complete isolation and they don't know anything about each other's processes. So we need a way to facilitate that communication. Secondly, we need our containers or services to start up in a specific order. For example, the manager needs to connect to Postgres first before being able to serve the dashboard. And it also needs to send data to our Redis cluster. And the flag bearer depends on being able to connect with Redis and the manager as well in case the data store is not filled yet. By using Docker Compose, a Docker network is automatically created for us. And its built-in DNS resolutions allows our containers to communicate with each other. The Docker network also allows us to control our services exposure to the broader internet. So for the Redis and Postgres database, for example, that shouldn't be accessed by anything outside of the network. We can also define which containers depend on one another so that the containers can start up in their respective dependency order. And once the developer configures necessary environment variables, Fana platform can be launched for use. Alternatively, developers who want to leverage AWS's managed services have the option of using Fana's Cloud Development Kit, or CDK for short. And CDK is a framework that allows developers to specify their infrastructure as code and deploy their application. Fana's AWS stack would be something like as shown. We have our Fana manager and bearer container managed by the Elastic Container Service, or ECS for short. The containers will then be connected to their respective RDS and Elasticache databases. And they will all communicate with each other through the virtual network called Virtual Private Cloud, or VPC for short. By creating a VPC for Fana and adding appropriate security groups, we can customize the network configuration to allow appropriate traffic through our Fana platform. And finally, we chose to include a load balancer to help us route external internet traffic. So how does our load balancer know where to send the traffic to? To configure our load balancer, a listener was added to handle routes for specific path patterns. When a developer wants to access the dashboard, they can make a request using the route path, and the load balancer will route that request to our dashboard. And when the SDK is making requests using path starting with /connect or a stream, the load balancer will forward those requests to the flag bearer to handle them appropriately. Before we move forward, there was one additional decision to make to finalize our AWS stack. AWS's ECS is a container orchestration platform. That is, it manages the lifecycle and placement of the task or the instances of our Docker images, but we need a service that can actually run our containers as well. The options we have are EC2 or Fargate. With EC2, the developer will need to deploy and manage a cluster of EC2 instances to run the relevant containers. And while this allows for greater control over the machines, it increases developers' responsibility to provision, scale, and secure these EC2 instances. With Fargate, though, there's no longer the need to manually provision the compute instances. Developers can simply create a cluster and specify resources like CPU and memory. And when the containers are deployed, Fargate will run and manage the servers to meet the necessary requirements. As Juan discussed earlier during feature flag implementation options, it was important for the Fana platform to be an easily maintainable solution so that the engineering team can focus more on the business needs rather than the task of managing a feature flagging platform. Therefore, hosting the containers using the Fargate service was more appropriate for our use case. So now that we've established our stack and the decisions that led to them, let's walk through how we can use CDK to deploy this architecture on AWS. There are two different stacks defined in our CDK. The Fana shared resources, which pertain the VPC, a new instance of a RDS, as well as a Elasticache Redis cluster. And these shared resources are referenced in the Fana's platform stack, which contain our containers, the load balancer, and a security group is defined here as well. And we can deploy both the stacks using CDK deploy all. And once deployed, we can reference the output for the load balancer DNS address to access our application. Here, we can see that our load balancer directs the route path to our UI dashboard. And we're also able to provide this URL as the bearer endpoint for the SDKs. And the load balancer will listen for those appropriate routes and direct them to the flag bearer. And now that we see how Fana is set up and deployed, Rob will discuss some additional engineering decisions and challenges we've encountered in arriving at our solution.
Thanks, Yoorhim. I'm going to talk about some of the technical directions we took, specifically how we tailored our respective SDK implementations, why we pivoted from our initial database choice, and how we went about choosing appropriate communication patterns for Fana's purpose. So first, I'm going to talk about why we have distinct SDK types, and specifically how they work within different types of applications and how those distinct contexts influence their respective design requirements. We started with just a server SDK meant for back-end applications within your architecture. Because that application code executes within your system, we could get away with a more straightforward approach to flag evaluation. It worked this way. The SDK would receive a full rule set object composed of all flags and their associated audience conditions, and then individual flags could be evaluated on demand. However, there's an issue with this when we move to user-facing client applications like websites. The problem is that rules can very easily contain sensitive information. If you're targeting by emails, if you're targeting by names, if you're targeting by other personally identifying account information, all of those values are exposed in that rule set object that's delivered to the SDK. So of course, it's not acceptable to expose that to every user visiting your website. Our solution in the case of client-side SDKs was to evaluate our flags before delivering them. So that process looks like this. The flag bearer would receive the user context object from the SDK. It would then request the full rule set object from the Redis store, and then it would evaluate that rule set against the user context. Ultimately, the client SDK initialization concludes with the SDK receiving an object composed only of flag keys and their Boolean values. This flag evaluates true, this flag evaluates false, etc. So this alleviates our privacy concerns, but this pattern requires upfront evaluation of all flags in the application. Depending on your app, it's very likely this includes flags won't ultimately be executed. So this pre-evaluation imposes an additional load on the flag bearer. But since it also helps secure that potentially sensitive information, it was a worthwhile trade-off. To reinforce this security, we use SDK keys to verify requests. SDK keys serve to authenticate those SDK initialization requests. They ensure those requests originated from an appropriate source. Because the client SDK key is visible in the request, any user can see it in their browser. If there was only a single key for both client and server, any request to the server endpoint using that publicly visible key could retrieve the full rule set with all its sensitive information. Having separate SDK keys helps avoid this by denying requests that don't match the proper key type. And next, I'll talk about the database conversation. The first iterations of Fana were built on Mongo for two primary reasons. First, without schema constraints, the structure of our data could change freely as the approaches evolved in early development phase. And second, Mongo's Atlas platform allowed us to host our data online, and that was very convenient accessibility for collaboration. But as our data model took shape, we realized it needed to express relationships between dynamic data. Nearly all of the operations on our data leverage those relationships between flags, audiences, attributes, etc. We needed to maintain consistency within relationships between changing data. It made sense to move to a database optimized for aggregating and extracting data across tables. It was more clearly a SQL story, and ultimately we chose Postgres for its familiarity as an open source solution. The last challenge I'll talk about was the communication between our architecture's components. One of the primary requirements driving that decision was evaluating our data in real time. The reason real-time updates are critical to Fana goes back to the core dynamic for choosing a feature flag platform for testing in production in the first place. Part of that is that time is critical. Specifically, if something goes wrong, that issue's impact on users is a function of the response time to that issue. In other words, rolling back bad code as soon as possible is essential. And perhaps less critically, but still important, flags ideally should be evaluated against the most recent data. So there's two steps on our data's distribution journey. The first step was getting the flag rules from our database to the flag bearers. And the second hop from there was getting those flag rules out to the SDKs. So the first decision we needed to make was with regards to how distributing the flag rules to the bearer would be handled. As I just mentioned, it was fundamental that the flag bearer receive data updates in real time. We considered three options to get there. API requests were a familiar pattern. A consumer makes a request, a provider responds with the requested data. But this pattern is conceptually backwards for our needs. The bearer initializing communications means the origin of the request is not where the data changes. The only way for a consumer to assure its data is fresh is to make a new request. In other words, a request is made every time the rule set is served to an SDK. And we realized we could do better. So webhooks were the first event-driven model we considered, and it met a lot of our requirements. Updates pushed to the flag bearer when they happened, and because it's in real time, the bearer no longer has to make requests to the manager. It already has the fresh data set, and that assurance allows us to cache that data set, so we can get all the benefits of that too. However, as the bearer scales, so too do the webhook consumers registered with the manager, and this strongly reinforces coupling of those components, which is what we're trying to avoid. Ultimately, of course, we went with a different event-driven approach, the pub sub. As Yoorhim mentioned, with this model, the manager now published to a single message broker that distributed messages to all flag bearer instances. Flag bearers subscribe to topics, or you could think of them as channels, published by the message broker, and they would receive messages along those channels in real time. So now both the manager and the flag bearers were concerned only with this single pub sub service, And this represented the level of decoupling we were looking for in order to accommodate the scaling needs we anticipated. The second half of the real-time update story was the communication from flag bearer to the SDKs. We needed to ensure flags were evaluated at the application level with the most recent data. Again, we considered 3 options. Polling was one naive way by which to approximate real-time communications. SDKs make requests to the flag bearer at specified time intervals, but this really just presented a choice between compromises. How close to real time do you want this to get versus how many requests do you want to hit your flag bearer with? WebSockets, on the other hand, were an authentic real-time solution. They offer 2-way event-driven communications between the flag bearer and SDKs. However, they were a little more complex pattern than we needed. We really only needed to go one way from the bearer to the SDK. And a more critical issue is that WebSockets will not automatically attempt to reconnect if the connection is dropped. A better option was SSEs. SSEs offered a one-way real-time channel from flag bearer to SDK. What this meant for Fana specifically was that when a flag is toggled off, the flag bearer can forward that updated flag status to the SDKs by way of the currently open and ongoing SSE connections. This ensures that a feature that needed to be rolled back is disabled as quickly as possible. Additionally, SSEs have built-in recovery with regards to dropped connections. So ultimately, because this was simpler and more resilient, this was the best fit for our needs. To close things out, here's a brief look at what future work on Fana might be. Right now, the biggest opportunity to reduce latency at runtime for apps using Fana is within the communication between the application and the flag bearer. So we could cut that significantly by hosting flag bearer instances on the edge closer to users. Launch Darkly executed this for 10 times faster SDK initializations. We could also utilize SDKs to relay metadata back to the flag bearer. So we could profile data like flag evaluation frequency and result values and help alleviate tech debt by way of identifying stale flags. And that's Fana. Thanks for listening. We'll open the floor to questions. What did you find most interesting when building this out? Audrey, do you want to start us off on that one?
Sure. I'll actually kind of continue on one of the points in the future work section that Rob was talking about. So he mentioned that Launch Darkly was able to reduce their SDK initialization time significantly. So in our research of Launch Darkly, they did this by moving more of their functionality to their content delivery networks vendors. So for better global reach and reduce that latency time. So we actually did go through a couple different diagramming iterations of our architecture to figure out what this might look like for Fana. So the flag bearer being that reverse proxy component responsible for managing those streaming connections with SDKs, we would have been able to move that logic, that function that evaluates the flag data, to something like a serverless function on the edge, on an edge node like on AWS or a Cloudflare worker, and potentially use some sort of data store at the edge, like a Cloudflare KV to hold the flag data. We were really close to implementing this. I think this definitely would have been a real possibility for us if we had a little bit more time, but this eventually would have kind of helped separate concerns a little bit better so that the processing logic is fully taken out of the flag bearer, and then its only role is just managing those SDK connections. So that was something that we were very keen on and very interested in implementing, and there was a lot of evidence based on some of our research that definitely would have been possible and fit our use case really well. I will let Juan, do you want to just pipe in really quick on this question?
Sure. So for me, it was definitely the dashboard. Really enjoyed working with React, and working on it in like a real project like intended for developers was really great. And I also like put a lot of effort into making it good for non-developers as well. So like adding in a bunch of little convenience features. It was just a lot of fun to work on, and also being able to communicate with the manager. Um, just like kind of figuring out like the front and the back end, like designing the API endpoints and like the shape of the data that we pass back and forth. Like that was it was like a lot. It was really fun to work on actually. So definitely really enjoyed that part. Yoorhim, what about you?
Yeah, I most enjoyed having engineering trade-off conversations as we're building Fana, especially the heated ones that really force us to consider, the strengths and weaknesses of each solution. I think the most memorable one we had were related to something Rob had mentioned about SQL and NoSQL. It was an important conversation to talk through the implication of going with, one database versus the other, and thinking through what type of data and what shape is optimal for a dashboard and bear, not only for the current system that we were building, but being flexible for future evolution of our platform as well. So how about you, Rob?
Yeah, so mine's a little bit off of what Juan was talking about with regards to developing the API between the dashboard and the manager. So we built the manager in Go, which I'm personally in love with that language. But one of the interesting choices there was whether or not to use an ORM, appropriately named GoRM. So because we only have a single application accessing the database, it was really convenient to also control the structure, the schema from that same source. You know exactly at the application level what you're working with because that's where it's declared. But it gets like more interesting when you move to more distributed data access, like larger systems needing to maintain consistency and potentially disparate data models, right? There can be conflicts. And there's a lot of very strong voices in the Go community who work with their data on a much lower level, including straight up raw SQL. So that was an interesting space to visit for sure. We have another question. Was it obvious to you immediately that feature flagging would be worthy of an entire project, or did it happen as a result of exploring the space? Audrey, you want to take that one?
Sure. I think like we were definitely, we did spend a fair amount of time just researching different kind of areas of interest and different problem domains. But if you even Google like feature flags in the search bar and just the number of different vendors and solutions that come up, and if you dig a little bit deeper even to that, like the many different use cases of how feature flags can be used, and we only really covered one of those very many use cases, you can see that there's a lot of different ways that you can architect a feature flag platform. You can optimize it for certain things, and there's certainly a need for feature flags. I mean, in our presentation alone, we had 2 case studies. There was definitely a handful more that we came across in our research. So it definitely seems like using feature flags is almost, I wouldn't say a standard, but seems very common for developer teams to be utilizing in sort of their workflows.
Yeah, great. What was your favorite part of working as a team, working with a mentor, and working on this project that we just mentioned that? So what was your favorite part working as a team and working with a mentor?
I can try to tackle this one. I think my favorite part of working as a team, I think it was very evident that whenever we approached a problem, we each kind of approached it with a different lens. And so we're able to consider the different ideas or things that we like. If something I couldn't see, maybe, Audrey or Rob or Juan would be able to point out. And, having it forces us to have, conversations about trade-offs more as well, and thinking through more holistically about, what's the best solution. And so for me, that was my favorite part. I think it also is similar to like pairing and coding as a pair. It's difficult at first, but as you get used to it, you really see a lot of benefit to doing that, and having an extra pair of extra pair of perspective to add benefit to your project. And working with a mentor, I mean, there's so many great things. Emotional support, providing really industry level sort of perspective on different approaches as well. Some things that there's just some things that are hard to research, where you need that insider knowledge to get a perspective on things.
Yeah, I definitely echo everything that Yoorhim just said. Like, it's really like working on a team. It's like you just get the advantage because I know like everyone has a tendency to like tunnel vision in on like a specific solution or a specific implementation, and then like you have other people to like offer different perspectives, like they challenge you, which is a good thing because it forces you to kind of like think about what you're saying and like from a different perspective. And like working with a mentor is like similarly like it's a similar benefit to that, because like you have an industry professional who's like telling you like, hey, like this is a real thing in the in the tech world, or it's not a real thing. So having like that expertise like was completely invaluable, and really appreciate Rodney's help there.
Can you expand a bit more on how you used Redis in your implementation? It sounds as if it was used as both a cache and a pub sub.
Yeah, I can take this one. Thanks, Elaine, for your question. You're correct. We used it both as a cache and a pub sub. So I'm not sure if it's very well known that Redis it had like a pub sub, I guess like API interface that you can use. I think it's most commonly and ubiquitously thought of as like a caching store. But since we had already kind of made that design decision that we wanted to extract out that data layer, it seemed really convenient to also use that same sort of component of infrastructure to also handle the message brokering. So that certainly simplified it when it came to deployment. So we only needed one Redis image instead of maybe a Redis image and something else that would be the message broker. And definitely in our AWS cloud deployment as well, we can just utilize that same Elasticache Redis cluster for both uses, instead of having to manage and spin up another separate piece of infrastructure.
Why did you choose Golang for the manager platform? Was there any language features that made it the right choice for that feature? Well, I can take this. A lot of the things we were seeing as we were building up to this project was that a lot of it's used a lot in the web development space for backend services. And because the manager was holding a lot of responsibilities for our backend, the performance was not negligible. We built a rudimentary version in Node first, and it was definitely quicker. But also just the fact that it is so common in the space. It was just as arbitrary to build it in Node as Golang. So, why not get experience with that? And I think ultimately allowed a slightly simpler, a slightly more straightforward management of our data with its static typing and that coupled with the ORM. So I think those are the main reasons we decided to go with that.
We had one more question come in, and we'll answer this one before we wrap up. There was a question about the load balancer for the cloud deployed application. Can you let us know more about how you used the load balancer? Yoorhim, do you want to take this one?
Sure. So for the load balancer, we have used it by adding listeners that will listen to different rules for the path. And so, I think in one of the slides we had shown that, with the DNS load balancer, the root path, when it sees that a request is made with the root path, it'll direct it to our UI dashboard, which the manager serves. And then there we have specified paths for the SDKs to make certain requests to connect or to make a, SSE connection. And those requests are routed by the load balancer to the flag bearer to handle them appropriately as well. I hope that helped answer your question.
Okay, well, if there's any more questions, you can find any of us on GitHub and drop us a message. But thank you all for tuning